9.4, example 3. Again, before we dive into example 3, I want to talk about our next theorem, which is the ratio test. This is by far one of the most useful theorems that we're going to learn when determining if something will converge and the radius of convergence. Hence the name of the section, radius of convergence. So we're going to let the sequence a sub n be a series with all positive terms and the limit as n goes to infinity of a sub n plus 1 divided by a sub n is equal to L, where L represents any number. So again, you're going to take the sequence, plug in n plus 1, divide by a sub n, and another convenient thing that we like to do with the radius of convergence is we go ahead and slap some absolute values on it, because we can show that if it converges for an absolute value, then it converges absolutely, which is even better. And it usually makes the problems easier because you can get rid of a negative 1 to the n pretty easy that way. So the series will converge if L is less than 1. It will diverge if L is greater than 1. However, it's inconclusive if L equals 1. So if you get L is less than 1, you're good. You know it converges. If you get it's greater than 1, cool. Now you know it diverges. If it's equal to 1, this is where you're out of luck and you have to use a different test. That's why normally this is my go-to test. If I want to show convergence or divergence, I will start with the ratio test, unless I can see right away that it's going to diverge and I can use something else, or I can use the direct comparison test very easily. So example 3, we're going to find the radius of convergence of this series, n to the x to the n divided by 10 to the n. Now what makes this one difficult is it's really hard to use a comparison test because I don't know what to compare it to. So what we're going to do is I'm going to show you how to set up the ratio test, and hopefully, because it says it converges, L will be less than 1. So let's see what happens. So notice that a sub n is equal to n x to the n divided by 10 to the n. So a sub n plus 1 is going to be wherever I see an n, I'm just going to put an n plus 1. So again, wherever I saw an n, I replace with n plus 1. So if there's an n plus 1, you put an n plus 2. Right? You always put n plus 1 wherever you see the n. Okay, so now the ratio test says I do the limit as n goes to infinity. Throw some absolute values on that. A sub n plus 1 divided by a sub n. This is where you're going to need some space because we're going to get some fractions over fractions here. So I get a sub n plus 1 is n plus 1 x to the n plus 1 divided by 10 to the n plus 1 divided by a sub n, which is n times x to the n divided by 10 to the n power. So now we got fractions within fractions, we got exponents rolling around, so we're going to do a little bit of work and clean this up. So this is the limit as n goes to infinity. Now let's just focus in on this top piece. This is going to be n plus 1 times x to the n times x to the 1. So what I'm doing is I'm splitting up that power, and I'm going to do the same thing in the denominator. So now what we're going to do is we're going to take a look at that bottom piece, which was n times x to the n divided by 10 to the n. And because it's a fraction divided by a fraction, we're going to go ahead and flip that and then multiply. So we're going to multiply by the reciprocal. Okay, so when we do that, I knew that it was going to cancel, and that's why I split up the numerator. So look at this. The x to the n's, gone. The 10 to the n's, gone. The n's don't cancel, but that's okay. So then I get that this is the limit as n approaches infinity of n plus 1 times x divided by 10n. And I'm just going to do a little bit of rewriting. So notice how I'm only dealing with n's. So anything without an n can get pulled out of that limit. So it's x over 10 times the limit. Oh, I forgot the absolute value. I want to make sure you have that absolute value. As n approaches infinity of n plus 1 over n. And then using our n behavior model, we know that this is going to go to 1 because the powers are the same. So now I'm just left with the absolute value of x divided by 10. Cool. Pretty easy. Now that we've done that, we're going to go ahead and try to find the radius of convergence. So I know that if we want it to be less than 1, so I go absolute value of x divided by 10 is less than 1, because that implies convergence. So then I can multiply both sides by 10. I get the absolute value of x is less than 10. Then using the definition of the absolute value, negative 10 is less than x, which is less than 10. Which tells me that this series will converge if x is between negative 10 and 10. So the distance between here is 20. So r, which is the radius of convergence, is 10. Right? The radius would be half the distance between the smallest value and the largest value. All right, now on your own, I want you to go ahead and find the radius of convergence of this series using the ratio test. All right, so here we go. So what we're going to want to do is do the limit of a sub n plus 1 divided by a sub n. So is the limit as n goes to infinity, absolute value, a sub n plus 1 is going to be negative 1 to the n plus 1, 4x plus 1 to the n plus 1, divided by, and then I just copy a sub n again. So the negative 1s go away. They're gone because the absolute value. So now I'm left with this is equal to the limit as n goes to infinity. And then I know I'm going to need to split these up. So it's 4x plus 1 to the n times 4x plus 1 divided by 4x plus 1 to the n. Okay, so those are going to cancel off. So I get this is the limit as n goes to infinity of 4x plus 1. There's no n's to plug into, so it's simply the absolute value of 4x plus 1. So the last thing I need to do is go ahead and find the radius. So the absolute value of 4x plus 1 is strictly less than 1. So I'm going to use the definition of the absolute value. Then I'm going to subtract 1 and divide by 4. So that means in order for this thing to converge, x has to be between negative 1/2 and 0, which makes r 1/4. Basically, you take this distance here and divide it by 2.